Okay, thank you and hello to everybody. We are Alba, Hierro, and me, Oriol, Colomés, and we are PhD students from at UPC and Thimne, and we work together in the Confus group, which is a group that works with the finite element method applied to the fusion energy. And now Alba will explain the basics of this method, and later I will focus on our main research topics. So, Alba?
Thank you. Do you hear me? So we know that scientists have been able to model the physical phenomena through PDEs, through partial differential equations. And here I just plot a couple of them that are the both we are working with. And they model the solution of a pollutant in a fluid and fluid flows. So in order to develop new technologies or to forecast natural behavior, we want to anticipate the solution of this kind of equations. So since it's not possible to have the exact mathematical solution, either because it doesn't exist, or either because the domain is so complex that we don't even know how to pose the problem, we will conform ourselves by simulating it. And actually, we will conform in getting a quite accurate enough solution. So to do so with a computer, we use what's called the numerical methods. In particular, we use the finite element method. To explain a bit how does it work, I will put a very simple example in 1D. So this is a very simple partial differential equation. Well, it's so simple that it's an ordinary differential equation, and this is the solution. So what the finite element method does is to split the domain of the solution, which is, well, there is no laser, which is the line below, in elements, and then assume that in each element the solution is a straight line. I'm putting this very simple, it's a bit more complex. But the result of this is that the PDE becomes a set of linear equations, and that this can be transformed in a matrix vector problem which can be solved with a computer. So if I split the domain in 4 parts, this is the result that I obtain. In this case, the result is not very good, but we know that if we refine the mesh, I mean, if we do the elements small and small every time, we will converge to the exact solution. So this is how it works, and this example is very simple. And just to show you that it's in fact very powerful, we will just mesh a more complex domain. This geometry is the chassis of a 3D director car, and we just downloaded it yesterday and meshed it and obtained this. And this can be used to compute the solutions of partial differential equations on this kind of mesh. And to solve this kind of problems, then, we do not only need to compute the methods, but we also need to use parallelizing codes, as the previous talks have presented before. And actually, the meshing of this kind of geometries is a complete field by itself. So this is just to put you on situation of what kind of methods we use, and my colleague Oriol is going to explain what we exactly focus our research on.
Coming back to one dimension, here we have, as Alba has said, the finite element method not always give a good solution. As we can see in the next slide, this is an unstable solution. And me and Alba work on stabilized methods to remove these instabilities. What are stabilized methods? It consists on modifying the method using some numerical tools in order to remove these oscillations. And well, there are a lot of causes that produce instabilities on the solution. But in particular, in this image, the instabilities are produced by the presence of the shock, which are these jumps on the solution. And Alba in particular is working on the shock capturing field, which consists on adding some artificial diffusion on the method in order to remove the instabilities to produce a better result like this one, where the solution is stable, so we don't have oscillations here. In my case, I work with turbulent flows, trying to capture the small scales of the flow, and I'm able to get better videos than much cooler videos than Alba's plots. But here we plot the vorticity isosurfaces that I will not explain. I'm not going to explain in detail. But what I can tell you is that if we don't use a stabilization method, the solution somehow would explode. And if we overstabilize the method, we wouldn't be able to capture these small features that appear in the middle of the cube. So at the end, we want to use all these numerical tools to simulate the physical phenomena that takes place in a nuclear fusion reactor, like the ITER, which is this machine that you can see here. And in particular, we want to simulate the plasma physics that takes place inside the tokamak. But this problem is really hard to solve, because this is plasma, real plasma, and not only because of the geometry, which is very complex, but also because there are a lot of equations coupled together. So in order to solve these problems, we have to use high performance computing methods that has been explained before also in supercomputer machines like Mare Nostrum. And well, that's our work. So thank you very much for your attention.